Hello and welcome to the Superposition Guys podcast. My name is Yuval, and my guest today is Andrea Tabacchini of Quantum Brilliance. Quantum Brilliance develops compact, room-temperature, diamond-based quantum accelerators for edge applications like robotics and satellites. Andrea explains their nitrogen-vacancy center technology, enabling stable qubits without cryogenic cooling. With innovations in deterministic defect placement and scalable nanoelectronics, they aim to launch a commercial 60 to 100 qubit quantum computer by 2029. We discussed their vision of small, low-power quantum processors working alongside classical systems, the growing investment driving practical quantum applications, and much more. We hope you enjoy this episode. Hello, Andrea. Thank you for joining me today.
Hi, Yuval, and thank you for the invite. This was a very good opportunity. Thank you.
Of course. So who are you and what do you do?
So my name is Andrea Tabacchini. I'm Italian as origin, as you can probably tell from my accent. And I work at Quantum Brilliance. I'm based in Sydney, and I've been with Quantum Brilliance for almost 2 years now, actually 2 years next week.
What does Quantum Brilliance do?
Quantum Brilliance is a quantum technology company, originally founded in Australia and currently split 50-50 between Australia and Germany. Our main focus is quantum computing based on something we call integrated quantum chip, which is a small room temperature chip. I can talk more about it in a little bit. We have been born as a full stack company, so doing hardware and software, and we envision basically a future of quantum computing everywhere. This is a bit of our uniqueness. And when I say quantum computing everywhere, I really mean everywhere beyond what people may think about quantum computing. And the reason being is that our room temperature small chip enables for a very small quantum computer respect to most of the competition out there. And this very small quantum computer, the size of a lunchbox, maybe the size of a nowadays single PCIe slot GPU, enables new use cases at the edge. For instance, in robotics, autonomous vehicles, satellites, a bit of everywhere. So this is what Quantum Brilliance is a company that envisions a future of small compact quantum accelerators deployed everywhere.
What is the underlying technology?
Yeah, the underlying technology is NV centers. Basically, our qubits are built out of defects in otherwise perfect carbon structure. The fact that the qubits are inside this carbon structure protects them very much from a lot of noise sources and environmental disturbances. And that's what really enables NV centers to be used as qubits at room temperature. It allows for long enough coherence time to not have to need to cool down to cryogenic temperature or anything like that. And if I may say something more about that, NV centers have been around for decades now. They've been used in research, universities, academia. They've been used as sensors. Really, what was the challenging part to make it a quantum computer is deterministic placement of these defects. Because at the moment, or so far, until Quantum Brilliance came out with its inventions, the technology to build NV centers was basically stochastic. So you just basically stochastically get some NV, some qubits if you want, here and there with spin needle aligned in a random direction, and you just need to hope that there are two very close to each other and then you have two qubits. But our innovation is really the key for Quantum Brilliance to be able to predict this future of small computers running at room temperatures based on NV centers is the fact that we have IP proprietary innovations in terms of two areas. One is the fabrication at the nanoscales. the qubits needs to be really well spaced at a very small and specific distance with each other to enable entangle but not disturbance, as well as scalable nanoelectronics. In these two areas, we have made innovations that is proprietary, and that's what enables us uniquely to build this type of technology.
You mentioned scalable nanoelectronics, and that leads me to my question of how do you control these qubits?
So yes, that's a very good question. It's like I said, there are two areas of innovation because it seems that if we can solve the nanoscale fabrication, which is already a challenging enough problem, then one is done, but one is not done. Obviously, the other area of innovation is in fact scalable nanoelectronics. Uh, as of today, for small qubit numbers and for sort of benchtop experiments or academic research, the typical ways to address qubits is by using microwaves and then basically confocal microscopes for reading the qubits. This is obviously something that does not scale, definitely does not scale into a chip. So we had to deliver some innovation there. Because when you think about placing many qubits next to each other at a very small scale, obviously having to address them individually, as per definition of a quantum computer, it requires something new, innovative that can be placed on a chip. And we have done some innovation and invention in the field of photoelectric readout, and that's what enables us to put these nanoelectronics layers on top of the diamond and microelectronics on top of the nanoelectronics, and then the photonics layer, the magnetic layers, everything packed into one single chip. I can't say more about how we do it, but that's kind of like hopefully it's answering the question.
How many qubits do you have today on a chip?
Yeah, so today, like I said a minute ago, today we have small we only have 2 qubits, and those are not on this type of chip that I've just described. These qubits are on a small diamond, the size of 1 millimeter by 1 millimeter by half a millimeter thickness. So it's really, really tiny. But we are still using confocal microscopes for the readout. This is a benchtop experiment that allows us to study the qubits features, the traceability, the integration, how to control them, what is the noise, what are the models, what are the error corrections that are needed, etc., etc. And this enabled some of our partners to also explore similar aspects of the quantum computing stack. We're going to move into chip soon. The roadmap hasn't been released yet, but as part of a big contract we have received in Germany from the German Cyber Security Agency, we are going to deliver a mobile quantum computer prototype in less than 24 months, and there will be milestones between now and there with at least 2 drops of qubits on chip in many more than 2. And those are going to be our first functional qubits on chip with the whole stack of microelectronics and magnetics and everything else on the chip itself. So it's going to come soon.
Help me understand. You mentioned that these 2 qubits you control with a confocal microscope, but that you're moving away from that. So if the new chip does not use a confocal microscope, then why is it useful to study the behavior of the existing system?
Well, the confocal microscope versus photoelectric readout is just a way to read the qubits. But the qubits are the same. The technology is the same physical entity, and therefore you can study and learn pretty much everything about the qubits with this sort of like more accessible, more benchtop kind of experiment.
When you talk about structure defects, which is almost a contradiction in terms, right? But I understand the need. what is the connectivity? How many qubits can each qubit, or will each qubit be able to interact with?
Yeah. Uh, so our vision is maybe I should start from where we want to get to first in terms of commercial valuable products. By 2029, we want to release the first compact quantum accelerator with commercial use. And this is also very unique to us because we are not aiming at 1,000,000 qubits on that chip. We are aiming at tens to 100 qubits. So we predicted with some analysis that between 60 and 100 qubits is what one need to add some commercial value out of these very small, very cheap, very low power consumption devices. Uh, the reason why we believe it's going to be commercial valuable is because of what we define as quantum utility. Maybe I can mention that later, not to derail too much the conversation. But the point I'm going to make to go back to your question is, so the first real commercial valuable product we're going to release is going to have tens to 100 of qubits. Uh, how many exactly and what type of topology and connectivity is something that we are still investigating. We've got a line of efforts, very R&D oriented, that is focused on not applications but algorithms specifically, and the hardware team working very close with them. So they are basically developing the two things in parallel, and the algorithm team that is working on the commercially valuable algorithms that can be run on these more qubits devices is going to inform basically the type of topology of connectivity and qubit number. Because it's important to say that with these atomic scale fabrication techniques, then we have freedom to place qubits really whichever shape we want. So qubits meaning defects. And therefore that will enable a large flexibility to accommodate whatever are the needs coming from the algorithm discoveries.
You mentioned tens to 100 qubits. Can you give me a sense of what kind of algorithm this is? Or is this a machine learning? Is this a prediction? Or more generally, is this an algorithm that you could, I guess, run on other types of quantum computers, except that they're not as small or power efficient and therefore maybe not as portable on the edge? Is that about right?
Yeah, look, we have three lines of effort in, we've got three different targets that we are exploring with the quantum algorithm team. I can't really disclose quite yet because we are at a bit of a critical stage there. But we are talking about algorithm as well as modalities. So we are investigating a bit of everything. So what will come out from this team may not be gate based, for instance, or might be gate based. We are exploring a bit of everything there, and there are these three lines of effort that unfortunately I can't disclose. But hopefully, in 6 months' time or so, we're gonna have something to announce or to publicly disclose. The other thing I wanted to say, well, it's slipped my mind. But I'll stop here.
Do you feel that you're going to need error correction for this application, or not really?
It's a very good question, and actually made me remember what I wanted to say about the previous one. You asked, I didn't answer your question about algorithms that we are developing being useful for other technology as well. Yes, potentially, yes. These are algorithms that obviously they can be potentially useful for other technologies too. The two aspects to consider is are one is the commercial value really comes from in this first generation of commercially valuable products will really come from the fact that these computers are very small, very cheap, and very low power consumption, such that you can employ 10 or 20 or 30 to solve your problems. And other technologies, they struggle in selling 20, 30 computers in a single rack with a low power consumption. So that could be making those algorithms not really commercially valuable for other technology. And the other aspect to consider is that because of this very tight development between the algorithm team and the quantum hardware team, uh, it may turn out that the modality and the algorithms specifically will be tailored for this first generation of commercially valuable quantum computer, which could also be a bit of a limiting factor. It is only true for the first generations. Now, going back to your other question, which is obviously very interesting and everybody asks, fault tolerant quantum computing, are we considering that? Are we considering error correction? Obviously, with very low qubit numbers, we are not aiming at fully error corrected uh, architecture or modalities. The power, the commercial value, and the power of these type of small quantum computers will come from the fact that are either going to deploy it in parallel, like in tens or more, and leveraging the parallel quantum computing advantage there, or that they can be deployed at edge, for instance, in very small piece of hardware or in submarines or things like that. Places where otherwise you don't even imagine to place a standard quantum computer. However, we are building a roadmap for fault-tolerant quantum computing. Uh, it's really too early to talk about that. But in the medium term, in the short medium term, we're gonna have these non-error corrected small qubit numbers compact quantum accelerator coming out for commercial use. In the medium to long term, we are going to have a version that may have many more qubits and error correction techniques that are viable to make these small computers full tolerance.
You mentioned that the computer is the size of a lunchbox, but the core itself is about a millimeter cubed. So what's taking up the rest of the lunchbox?
So when I mentioned the 1 millimeter cube, roughly 1 millimeter cube, that's the size of the diamond itself that we have today. Once we add the nanoelectronics, microelectronics, and magnetic and photonics layer, that could get up to the size of maybe a centimeter or two. Still, is very small with respect to a matchbox or standard GPU today. Everything else in there is basically the electronics, control electronics. When I say that it's going to be a lunchbox, I mean everything is in there. There's no need for anything else to run the computer except to slot it into a PCIe slot or something similar. And all is needed to run, read, and control the qubits is inside there. So basically, that's control electronics.
One would assume that this could ultimately be smaller, right? A quantum computer in your pocket.
that's that's a very good that's very good vision. It's certainly something that we keep in mind. That's probably stage 3, maybe. It certainly has the power to scale down this type of technology, right? Because the chip itself is where the quantumness happens and is well patched there. So yes, I guess that it's just an engineering problem after that. How small can we make the control electronics, and uh, yes, how small can we make the whole packet? It could may as well end up in a laptop in the future.
As you think about the last 12 months, what have you learned about the quantum computing market or envy centers that you didn't know a year ago?
Yeah, so I have to say that in the last 12 months there have been quite some movements in the market for quantum computing, right? Uh, Companies that are public, they had their share prices going very much high and very much down and then back high. Um, so I have to say that it's not just hype. I don't think it's just hype. I think that there is something happening, and that's proven by the fact that a lot of private investments are still flowing to companies. For instance, QE recently closed a very good round. Congratulations to you all. But other quantum computing companies also closed quite big rounds recently. So uh, I wanna just put it there. That is, I don't believe it's just hype. I think that there is something, and there is some trust, and there is something that is coming out. I also think that a lot of the big discoveries that are going to change the market are still happening, even though they are not maybe publicized as much as the Google, Microsoft, or Amazon's news. What else I've learned? Uh, yeah, I think that these are the big takeaways, and we're not entering into quantum winter as people have speculated a year or two ago. I think that the next couple of years are gonna be really uh, interesting for our industry.
You mentioned some big companies, and it seems like in the last couple of weeks, their CEOs got into the habit of opining on when will quantum computers be useful. Do you want to contribute to that discussion?
From our point of view, like I said earlier, I think that we are going to have some useful quantum computer in 2029 when we release our first product. I don't want to really challenge other companies' roadmap, but there are multiple companies that are talking about 2 3 years time, and I don't feel they are really direct competitor for us because our feature is very unique, and the future I envision is one where big quantum computers with millions or billions qubits they work in hybrid modes together with GPUs, CPUs, and also racks of small quantum computers like our, because they're maybe more suitable for some specific tasks. So yes, I think that I would say in the next 5 years. However, the specification needs to be made here is what does it mean useful? For me, useful is it really makes you save 5 cents per operation on a specific, very well defined use case only. That's already useful. What people have in mind when say is useful quantum computer or quantum advantage and what's not is more something like general general usage quantum computer. That could have to wait a bit longer.
What kind of companies are interested in quantum computers at the edge?
Yeah. So uh, edge quantum computing is something that is uh, very early. Uh, while for most of other cases or use cases of quantum computer, everybody's talking about them, and there is a common understanding of what are those use cases and what quantum computers can be used for. For edge quantum computing is really just us talking about it. And we haven't made a big effort in terms of marketing so far. We're going to change that very soon, but without that, there isn't much conversation going on. Really, it's just really our own personal riches onto Brilliance. The typical use cases are obviously you can think about defense and military applications, where you have to elaborate information or images, maybe large images, need to do quantum machine learnings and things like that at the edge without having the possibility to transmit information to a data center or to larger compute capabilities for different reasons. Maybe you're in a submarine, or maybe you're in a war zone where you really can't communicate. That's obviously the most obvious use case. But autonomous driving, maybe not the first generation, but a future generation may require some quantum acceleration next to classical acceleration given by GPUs. Satellites may need the same. Our solution, like I said, is very low power consumption. It can make it for a much more sustainable and power efficient solutions than using GPU only acceleration. Uh, I like to think about robotics, and I like that in general. Not just the cyborg types of humanoid type of robots, but also robots in the manufacturing lines where you've got maybe to analyze, for instance, defects on parts, and you don't have bandwidth to send images to a large computing uh, capability for analyzing the images. And these are the type of use cases that are most talked about.
In last hypothetical, if you could have dinner with one of the quantum greats, dead or alive, who would that person be?
I was obviously expecting this question, and I could I couldn't get an answer really for how much I thought about it. The two names I got in mind are Richard Feynman, because like I'm very fascinated by that figure, not just from the physics and scientific contributions that obviously was a genius and had a big role into quantum computing, obviously. Uh, but really, I think that if I had to choose one, it would probably be Einstein's, simply because in the last years he spent so much time trying to find a different explanation to reality that wouldn't have to involve these crazy quantum physics theories. Would be good to have him to digest where we got to in terms of scientific discoveries and quantum theory and see what he would envision. That would be, in my opinion, the most interesting opinion.
Wonderful. Andrea, thank you so much for spending some time with me today.
Thank you again for the invite, Yuval. It was really a big pleasure.